Hard. So today I will talk about AC power or power in AC circuits. If I can get to the right chapter right there. Okay. Let's see. AC power, power in AC circuits. Okay. So electrical power, you would have seen that electrical power is transmitted over long distance lines from the utility, the power stations, long distance transmission lines, going all over the mountaintops, going into cities and residences. In our San Luis Obispo, you'd have seen these around the city and going over the top of the mountains on the other side. Okay, so if you have driven down Highway 101, you'd see them crossing over the mountains. And inside the city itself, there are multiple locations where you can actually, view the overhead lines. One of the spots I always like to bring up is the parking lot where Sprouts is near the Madonna Plaza. Sprouts grocery store. Every time I used to go there, I used to park at a certain spot, and it took me until a few weeks later to realize that I was parking right next to like an overhead electrical line. Okay, so if you go to that parking spot or many other locations in the city, you can see those lines crisscrossing the entire city. Now, the reason I bring up the long distance is because if you think back to chapter 1, I spoke about resistance. A piece of conducting wire typically does not have any resistance, right? That is true when you're performing theoretical analysis. In real life, a piece of wire actually has resistance, inductance, and capacitance, right? But it does not rise to the level of interference. We could take a 100-foot long extension cable, plug it into the wall. It'll have some resistance, but not enough to drop the voltage from 120 volts at the input to, like, let's say less than 100 volts at the output. Does not work that way. Resistance, the equation for resistance is rho L over A. It is directly proportional to the length of the conductor. So when it's 100 feet or less than 100 feet, it does not matter. But when it's hundreds of miles long, it does matter. Okay, so long distance electrical wires run for hundreds of miles. And when the L is hundreds of miles, resistance increases. And that resistance does rise to the level of interference. And the interference it causes is basically the electrical power that is transmitted over these long distance wires. Much of, not much, but a lot of it is lost as heat. Again, electrical current traveling over long distance wires will encounter resistance. When you encounter resistance, that energy is transferred and is lost as heat. So anytime electrical power travels over long distances, a lot of that power is lost as heat. Okay. Even for our electrical wires, it is lost as heat. That is also one of the reasons why an appliance manufacturer, especially if it draws a heavy electrical load, will tell you not to use an extension cable. If you use, especially in the winters, if you try to plug in an electric heater into your wall outlet, they will tell you do not use an extension cord or a power strip. The reason is because all consumers would not pay attention to the power rating of that power cord or the power strip. So if it draws too much current, that power strip or the power cable will get overheated, will short out the wires, and will spark and then do a lot of real damage. That is one of the reasons why that warning is in. Okay. Anyway, the way it relates to us in our topic of discussion for today is electrical power flows from the utility to the consumer. Consumer of two kinds, residential as well as industrial, right? Residential customers and industrial customers both run electric machines. For industrial customers, for residential customers, those electric machines with heavy loads are basically your washers, your dryers, perhaps your refrigerator or a freezer, and your HVAC units. Okay, those have spinning motors or spinning electric machines that have coils. An electrical conductor wound in a coil is an inductor. think about the washing machines and your dryers. If you have one in your apartment residence or in your house, in your homes, how many times a week do we run that? Maybe once, twice a week, perhaps, right? Unless you're running a commercial laundromat, those machines are only going to be run or used once or twice a week for a few hours at most. Versus an industrial customer where these machines are running nonstop 24/7. They do not have just one washer or dryer. They have hundreds of electric machines, and most of them might be running 24/7. If you're running a factory or a workshop, if it's not 24/7, it's at least 5 days a week from 8 till 9 or 8 till 5, whatever. Okay. So the residential versus industrial customer is a big factor when it comes to inductive loads. Okay. Residences have inductive loads, industrial customers have inductive loads, but the way they use these inductive loads and the amount of inductive loads is much, much higher for a industrial customer versus a residential customer. When we talk about inductors and capacitors for that matter, we talk about reactances, right? Because they're energy storage devices. So just as resistors have real power associated with them, so do inductors and capacitors. Because they have reactance, they have reactive power associated with that reactance. And that is where the big difference lies versus a industrial customer and a residential customer. Okay. Industrial customers have reactances to deal with, which are associated with reactive power. And this reactive power is a big deal. Okay. Reactance for an inductor and a capacitor is mathematically represented using the imaginary number, right? We worked with the complex numbers and imaginary numbers to do the mathematical representation of the reactance of an inductor and capacitor. So we will take that a bit further and also use complex numbers and imaginary numbers to represent this reactive power. Okay. This reactive power has a physical basis in real life. Okay, it is real. Similar to reactance, this reactive power is also real. But we use the imaginary number for the mathematical representation. So if you ever read or hear the words imaginary power or imaginary reactance, it is the mathematical sense, or it's a mathematical reference. It is not, it still has a physical basis. The reason this is important is because if you think back on the last few weeks, and I talked about how power for an inductor, energy in an inductor and capacitor flows in and out for an AC applied voltage or current. For a DC applied voltage, power goes from the source and into the resistor. Power goes from the source into the resistor or the inductor or the capacitor. But when it's AC power, because we are transmitting energy and because they're energy storage devices, power goes into the inductor, and then in the other half cycle, it comes out. So for an inductor, in the positive half cycle, it receives the power. In the negative half cycle, it sends it back out. For capacitor, it's the opposite. In the negative half cycle, it receives the power, and the positive half cycle, it sends it back out. We good so far? Right? So reactive power for an inductor, and we keep the capacitor on the side for now. The reactive power for an inductor flows in and then flows out. For every half cycle, it flows in and out. Now, if we take that concept and apply it to a utility and the industrial customer that is hundreds of miles away, this reactive power has to travel hundreds of miles from the source, which is the utility company, all the way to the industrial customer. And then in the other half cycle, it has to travel all the way back. Make sense? Again, in one half cycle, the inductive load receives the power from the utility company, and the other half cycle, it sends it back. And when you travel or you transmit power over long distances, we talked about a few minutes ago, a lot of that power is lost as heat. Okay. And in the case of reactive power, all of this is needless. because the reactive power is associated with that magnetic field. It does not do any real work. The real work is done by the real power, and that converts the electrical energy into mechanical energy. The reactive power is associated with the magnetic field, but it does not do any real mechanical work. Yet, again, it has a physical basis. So it is required for the machines to start up. So the utility company does have to send all of that reactive power. So industrial customers pay for the real power plus the reactive power. And not only does the utility company and the consumer have to bear the costs of the equipment, the installation, but every time it goes back and forth, they have to pay for everything that is lost. Okay, so obviously the solution would be that we do not have to send this reactive power. And fortunately, we have the capacitor, which is the exact opposite of an inductor, to help us with that. But let's take a 10-second pause. You think over that. Let me know if you have any questions. It would not be possible because the machines would not start up. So in this case, it would help if we just think of it as one combined entity. So real plus reactive power would be just one combined entity that is being sent over the lines, but only some of it is used for the reactance. The other one is used for the real component. Okay. All right. So obviously, we do not want to send the power back and forth over long distances. For those of you who have done lab 8, you did power factor correction. That is the technique we employ when we place a capacitor in front of the inductive load. Okay. So I stated power goes from the utility company to the to the industrial customer into the inductive loads. Next half cycle, when it comes out, you place a capacitor in front. Okay, the capacitor is already part of it. There is a technique, that there's a technique and calculations that are involved in this. Again, is a specialized topic of electrical engineering by itself, but you place a capacitor in front. And so when the power flows out of the inductor, it goes into the capacitor. And in the next half cycle, when the inductor requires power, it does not come all the way from the utility company. It instead comes from that local capacitor. And the power now bounces out of the capacitor, goes into the inductor, and then goes back and forth. So instead of traveling all the way long distance back and forth, you simply place a capacitor in front, and the power is now bouncing locally within that load itself. And this process of installing a capacitor or a bank of capacitors in front is known as power factor correction. Okay, power factor correction. The requirement of that power is given by the power factor, and the reduction of the requirement is known as power factor correction. Okay, so they have these huge capacitors, like big cylinders, and there's like an array of these capacitors known as a bank of capacitors or capacitor bank, and that is included in front of or installed in front of that factory or that warehouse or that workshop. And so instead of the utility company supplying all of that power, the capacitors supply that power. And so now the requirement for the inductive load is reduced. It still requires it when the switch is first flipped on. It still requires it from the utility company. But after it receives all of that power, beyond that, it's all supplied locally. So if the power ever goes out in a factory or a workshop, or if it's a new factory being installed, when the switches are first flipped, the utility company, so the industrial customer has to work with the utility company to flip on the switches one at a time. They cannot just flip all of the switches all at once. The system would be overwhelmed. The company would not send all of that power at all. Okay, they would not send that power at all. It's a campus like Cal Poly or an industrial environment, if the power ever goes out, they have to work with the utility company to flip the switches on one at a time. Make sense? So let's look at the mathematical equations. We talked about reactive power. So let's just go straight away to that first. Reactive power is represented by the letter Q. Okay, Q. And all of these are uppercase letters. Okay, we are already familiar with real power P. That is still the case. Real power P associated with the resistive component is still given by P, uppercase P. Unit is still watts. Reactive power is the new term noted by the letter Q. And the unit is volt ampere reactive. Volt ampere reactive. And because it is represented by the imaginary number, the total power, meaning you add a P and Q, is a complex number or a complex quantity given by P plus JQ, and it's represented by the letter S. Okay, it's represented by the letter S. So P, Q, and obviously the script R, because R is for resistor, they went to the next letter, which is S. And the unit for S, total complex power, is volt ampere. Okay, volt ampere. Volt ampere. P, Q, and S. P plus JQ is S. Again, it's simply P plus Q, but again, we are using imaginary number to represent it. So it's total complex power VA. And because it's a complex number, we can represent it as vectors and draw a triangle, which would be known as the power triangle. Real power P is on the x-axis. Reactive power Q is on the imaginary axis. And when you complete the triangle, you get the magnitude of S as the product of the RMS values of the voltage and current. It is known as the apparent power. Magnitude of S is known as the apparent power. VRMS times IRMS. If you think back to chapter 3, not chapter 3, sorry, chapter 5. An inductor has a positive impedance angle. Okay, for an inductor, the voltage always leads the current by 90 degrees. For a capacitor, voltage always lags the current by 90 degrees. So the reactance for a inductor is mathematically represented as a positive number, whereas the reactance for a capacitor is negative. And hence, the reactive power associated with both is also mathematically represented as positive and negative. In real life, obviously, power is never positive or negative. Power is just power, right? But mathematical representation, we use positive and negative terms. So for an inductor, QL is positive. For a capacitor, QL is negative. And you can see the graphical representation. If QL is positive and you add a capacitor reactive power, it's a complex quantity, meaning you take the phase angles into account. QC, sorry, that's QC, not QL. So your total power total reactive power is now reduced. So power triangle for the inductor, which required Q of this amount, can now be reduced if you place an appropriately sized capacitor in opposition. Okay, so now your power angle is reduced. This is a graphical representation. QL points straight up, QC points straight down. Your total is the difference between the endpoints. If it's linear, if it's a resistor, you would simply add, right? 2 plus 3 equals 5. Whereas an inductor and capacitor, if you add in the complex plane, you have to take the phase angles into account. And because the phase angles are opposite, you can balance out the reactive power requirement using a capacitor. Okay. All right, we are out of time. So there's one more slide of equations and example of problems that we'll do on Wednesday. Think on this, think on these concepts, and let me know if you have any questions. All right, I will see you on Wednesday. Yes. One full letter size page, front and back. For the final, right? Yeah. It's all there on the final exam page. So everybody should please make sure that you read through everything on that page and then reach out to me if you have any questions.